All right, today we're going to talk a little bit about efficiency today. How efficient are things, kind of thing. We get energy from different places, of course, physical, chemical, and nuclear processes. Physical processes such as just as simple as changing a state. If you change water from a liquid to a gas, or a gas to a liquid, or a liquid to a solid, or vice versa, okay, that's either going to require some energy or perhaps give off some energy, okay. For example, if you change H2O liquid into an H2O solid, so if you go from a liquid water to freezing, you give off a little bit of energy. You give off about 6 kilojoules of energy, okay. This changing a state, so when you change it from a liquid to a solid kind of thing, same thing, not making new stuff here, just like water from a liquid to a solid or something along that line. When you change it from a solid to a liquid, this is typically anywhere from about 1 to 100 kilojoules per mole of that stuff, of that type of energy that's involved there. So not a lot, 1 to 100, okay? And of course, if you remember from Chem 20, it's things about like talking about hydrogen bonding, things like that we're talking about here. Dipole-dipole, London forces, intermolecular forces, okay? If you're going to do an actual chemical reaction, so if you're going to take, for example, we're going to burn some butane or burn some propane, we're going to combust it, okay? Or if we're actually going to make formation or decomp or stuff like that, usually you're looking at about 100 to 10,000 kilojoules per mole of energy that's required or given off in some cases for that kind of thing. So there's that kind of part of it too. That's intramolecular, where you got to take things and break them apart and reform them into something new. Okay, so the carbons and hydrogens need to break apart, and the carbon's going to combine with the oxygen, and the hydrogen's going to combine with the oxygen, and it's going to give you new stuff. Okay, so that's usually anywhere from 100 to 10,000 kind of thing. We have nuclear changes involved, which involve the nuclei of atoms. Nuclear bombs, obviously, right? Nuclear changes typically involve massive amounts of energy. Okay, obviously, for example, like I said, nuclear bombs. 10 to the 9 and 10 to the 10 kilojoules per mole, so quite a bit of energy is released in those cases there. The sun produces energy by fusion of hydrogen. Okay, so you get negative 2.7 times 10 to the negative 9 kilojoules. Okay. Now we're going to talk about energy and efficiency. How efficient are things here? And well, let's take a look here. In every energy conversion, okay, leads to some amount of energy that's being wasted. Of course, not everything is it's not 100% efficient. Anything that we do, driving in our car, for example, yeah, you burn gas. Okay. You're burning gas, and you know, as well as I do, what is on average you get 30 miles per gallon kind of thing, right? You're not being as efficient as possible. A lot of that energy is lost as heat. That's why you have a radiator and coolant in your car to keep things, keep the engine not going too hot, right? To keep it cool. A light bulb turns on. Okay, like the light bulbs in this classroom, for example, or you know, even at home, you know that. You know, if you go to change the light bulb, it just burns out, and you go to change it, it's hot, right? You can't change it. You shouldn't. That's gonna feel like burning. Okay, that's what that feels like. You know, it gives off a lot. Yes, what's the purpose of a light bulb? Give off light, but it also, okay, doesn't convert all that electricity to light. It also gives off heat. Okay, so that energy is being wasted. It's giving off heat that is, you know, like I said, not part of that job there. In case you guys ever want to use this, feel free. If it's really cold out, if it's really cold out and you're worried about your car starting and getting here for period 2 chemistry, which I know all of you are, except for him. But you know, if it's really cold out, you take a light bulb, right? Some type of light bulb, and you plug it in overnight and put it underneath your oil pan, underneath your truck or your car, and you basically keep that engine oil warmer, yes? And then when you go to start in the morning, it's already warmer. It's easier to circulate and things like that, right? Batteries are a big part of that, of course, as well. But all right, so things like that. Really, if you're going to talk about efficiency, you need to talk about two parts to this. Okay, how efficient something is. Well, how much energy do we actually get, or how much energy is actually delivered, kind of thing. Usually you can calculate that by, for example, Q equals MC delta T, or delta H equals N delta RH, things like that, okay? That's how much is actually used in the process, okay? Then we have the total available energy. In other words, the ideal or the theoretical amount of energy that should be released from that chemical reaction. Or, and in that case, usually you're talking about Hess's law, and once again, delta H, N delta RH, okay? Really, this here, if you think about this efficiency thing here, you've seen this formula before, right? Doesn't this look like a lot like percent yield? Yeah? Experimental, how much you think you should get, how much you get in the lab kind of thing, compared to the theoretical, how much should you get, right? That's really what this formula is, experimental versus theoretical.
If you look for something that is like 30% of energy in the correct way and is 70% heat, and you have a system that absorbs some of the heat and then produces more energy with it.
Yeah, but you'll never be able to collect all of it, though. That's the thing. Yeah.
Does that count as more energy as possible?
No, no. I mean, just for our purposes here, we're just going to keep it very simple like this here. So you can think about percent yield, right? Experimental, basically, versus the theoretical. Even, you know, think about this. When you guys did your lab with the magnesium and the hydrochloric acid the other day, yeah? Right? And if you think about and magnesium oxide, that powder you weighed out with the acid, yes? We just did that, what, last Thursday or so? Yeah? You know, you guys got pretty small percent errors, right? I think, for most of you. Like I saw quite a few that were under 5 kind of thing. And that's good. But once again, that kind of goes to prove to you that nothing, right? It's not 100% accurate, right? I mean, yeah, there is a chance there you might have gone over or something like that or whatever. But theoretically speaking, right, you're not going to catch all that energy. You guys know that very well. You think you caught all the energy from those 2 styrofoam cups and a cup on top with a, you know, no, we didn't, obviously, right? That's not 100% efficient. If something was 100% efficient, by the way, gee, we'd probably solve a lot of issues, eh? Like, you know, we'd have a lot of energy. Me too. I wouldn't be so sleepy, right? But we'd have a lot of energy, right? We wouldn't have issues that we have right now trying to be, you know, why we're making hybrid cars? Because we're trying to make it more efficient, right? Et cetera, et cetera. The thing with efficiency is you have to keep this in mind. It's actually a little bit easier than percent yield because you always know where the numbers go. Because what's the difference between efficiency and percent yield? What would be the difference if you looked at those formulas? Right. So percent yield, you would get over 100. You could get over 100%, right? I mean, that could have even happened in your last lab, although it shouldn't have, but it could have, right? I doubt we collected more heat than we were supposed to. That's probably not the case. But, right, with efficiency, nothing's 100% or over 100% efficient, right? So we always know the smaller number goes on the top, and the bigger number always goes on the bottom, right? So think about that when you're doing efficiency questions. Now, how many efficiency questions are you going to get? And the answer is probably on your test, maybe 1, maybe 2, probably 1, maybe. On your diploma, 1, maybe none. I'm not going to lie to you. You know, and I've told you kind of what, you know, what's important stuff here. Is this important? Well, not really. However, is it important in reviewing all the stuff that we know? Are we going to use this to calculate MC delta T stuff? Yes. Do we need to know delta H equals N delta RH? Yes. Should we be able to figure out where we're getting energy from, Hess's law, stuff like that? Yes. So all that stuff's still very important. Okay? All right, here's your first example here. Propane is a commonly used barbecue fuel. Okay? So you're going to use propane as barbecue fuel. Determine the efficiency of the barbecue as a heating device if you use 5.10 grams of propane are required to change the temperature of 250 grams of water, 500 grams stainless steel pot from 75 to 75 degrees Celsius. Okay? So a lot of stuff there talks about efficiency. A lot of numbers. Where do we start? That's the question. Well, let me ask you this. If we're talking about efficiency, when you see this word here, you need two parts. You need how much energy was actually taken in and how much energy was actually produced, right? It's still an energy lost, energy gain thing, right? But we're comparing how much energy was lost, how much energy was given off, to how much energy was actually taken in. Okay? We're comparing those two now. We're not necessarily saying the energy lost equals the energy gained. No, no. We're saying there's two different parts here. Okay? Now to do those questions, energy lost equals energy gained, we have to assume that we're collecting all the energy. That's probably not going to happen. Okay? So you really have two parts here. Theoretically, let me ask you this. If I took propane and I burned it, how much energy would I get out of that? Do that now. If I took some propane and I burned it, how much energy should I get out of that? And you can start with the very basic stuff. I got some propane, I burn it. How much energy do I get? So for right now, let's just say, how much energy do I get out of burning some propane? Propane. Propane. Jimi Hendrix. We're not gonna get past there. For tomorrow, though, this is what I want. I want you guys, balanced chemical equation, delta H, yes? I want you to figure out, for me by tomorrow, okay, we shall check, hey, if that's the balanced chemical equation, if I'm using 5.10 grams of propane, how much heat was actually produced by using 5.10 grams of propane, right? Okay, so I want you to include that now after you get the balanced chemical equation. I want you to figure out how much heat was actually produced by burning 5.10 grams, okay? And then we'll stop there for today. Tomorrow we'll talk about the rest of this. We'll do the other example. We'll give you some homework. We'll go to mass, and